Have you ever wondered how to make your own physics simulated vehicles? Raycast vehicles are often used in games to simulate cars very well, while being simple and very performant at the same time. Understanding and implementing your own is very useful, because you can then adapt to any situations you might need. So let's take a look at how they work and make our very own arcade-style car controller. In this first step, we'll take a look at how the car suspension works. First, let's take a look at how a real spring works. A spring is very simple. It has a rest position where it wants to stay, and it applies a force trying to push or pull it towards that rest position. This force is given by the offset distance times the spring stiffness. That's how powerful or beefy the spring usually is. The stronger it is, the higher the force. Applying this force, now our spring will keep oscillating up and down. To prevent it from being so bouncy, real car suspensions uses what is called a damped spring. You can think of this as if the spring have to pass through a very viscous liquid. The faster the spring is moving, the harder it makes it to move. So we reduce the spring force by the damping strength, how viscous this liquid is, times how fast the spring is moving. A high damping value will make it stop faster. But make it too high, and it will actually slow down the speed the spring returns to its rest position, which is what's called an overdamped spring. There is a way to know how high these values can be before it affects the returning speed, but we'll look at that later. So playing around with these values, we can create a very good looking damped spring that looks very similar to a car suspension. A Raycast car is called like that because it uses Raycast pointing down instead of wheels to simulate the spring suspension interaction. The car itself is just a block, and the suspension forces are what are actually keeping them above the ground. Now knowing that, let's start making our car. Here's our humble scene, just a floor and some cameras. A Raycast car is completely physics based, so let's start by creating a new rigid body 3D. Let's put it above the ground and create a mesh instance 3D to display the car. Create a box mesh, and we'll be using 2 for X, 0.5 for Y, and 4 for Z, making it about the shape of a car. I'll also add a material just so we can have some colors to look at. Then let's make another mesh instance 3D and put it at the back of the car. I will use 0.65, 0.4, and 1.8 for the size. This is just so we can know which way is the front and which way is the back of the vehicle. Then, let's add a collision shape 3D for the actual collision of the rigid body. Create a box shape and set the size to 2, 0.5, and 4, the same as the car body's mesh. Now it's time to create our suspensions. Start by creating a new Raycast 3D. Put it in the front of the car, about where the wheel spring would be. Here I am using -1.1 for the X and -1.3 for the Z position. And let's rename it wheel FL for front left. Then duplicate it to create a back wheel. I'll put this one in Z 1.3 and rename it wheel RL for rear left. Now let's duplicate both of the wheels and put them on the other side. And rename them to FR for front right and RR for rear left. With the car setup done, let's create a new script for the car, and let's call it Raycast car. We'll start by declaring an export variable wheels, which is an array of Raycast 3D to keep track of our wheels. For now, we will also declare a variable for the spring strength of 100, and another one for the spring damping of 2. And finally, the one for the rest position at 0.5. Since our Raycast target's position has a length of 1, the rest position of 0.5 will make it stay in the middle of that. Then let's create a function called doSingleWheelSuspension that uses a Raycast. And on the physics process, we will iterate over all of our wheels and call that. Now save the file and add our wheels to the script. Click on the add element 4 times and select each of the wheels to add them to the script. You can also drag and drop them if you prefer. Now let's begin with the physics. First, we need to check if the wheel Raycast is colliding. If it is, then we will apply forces to the car using the spring formula we just saw. We can get the contact hit point where the Raycast hits the ground with suspensionray.getCollisionPoint. We can get the spring up direction with suspensionray.globaltransform.basis.y. This is the direction vector that will always point up from the wheel's perspective, which is the direction that the spring can move. And to get how long the spring currently is, we use spring length equals suspensionray.globalposition.distance to contact. and our offset is the rest distance minus the spring length. So using the spring formula, our spring force is the spring strength times the offset. We convert that force value to a 3D directional vector by multiplying the spring force by the spring up direction, and we'll use that to apply forces to the car. Now, Godot apply forces uses an offset position instead of a global point. So our force offset position is the actual point we want to apply the force to, minus the global position of the rigid body. And now we can use apply force to apply our spring force to our suspension at the position where it hits the ground. Let's activate the debug collision shapes and play the game now. And we have a very bouncy car. You might have noticed a few problems with this. We can change the forces and see the results change. But first, let's implement our damping force like our 2D example. The damping force is the damp strength times the relative velocity, which is how fast the spring is moving. You can calculate the relative velocity by saving the previous spring position and calculate how fast it has moved. But physics already has a way to calculate that instantly. Godot unfortunately doesn't expose this function to the script, but we can easily make our own. So let's create a function named getPointVelocity that receives a point and returns the velocity that point is moving at. This function just returns the linear velocity plus angular velocity dot cross product of the point minus the global position. Don't worry about these values too much. This is just a commonly used physics formula, and let's make it return a vector 3. Now, for our damping force, we can get a word velocity by using the getPointVelocity with the contact point, and we can calculate our relative velocity, how much it has moved relative to the wheel's y-axis, by using spring up direction dot product word velocity. And our spring damping force is the spring damping times the relative velocity of the spring. Now we just need to update the force vector to subtract the damping force of the spring force before multiplying it for the spring up direction. And that's it for the main physics part of the code. Now our car bounces into a stop. We can adjust the values and see how it changes. Now, there's still one more problem we need to fix. You might have realized, but by using the spring formula as is, our car is pushed down when the Raycast hits the ground after the rest distance. This gives the effect of making the car stick to the ground. And while some old arcade games use this style, you might not want that. This is especially bad if you have ramps or loops in your game. When your car leaves a ramp, the back wheel's Raycast might pull the car at the back, making it flip more easily. Or you might stay stick to loops, even if the car is not moving. To remove that effect, you just need to make sure your rest distance is the same as the Raycast target distance. This way, the Raycast will only detect when the offset is negative. We'll take a closer look at this later, but first, let's give our car some real wheels. Select the wheel Raycast and add a new mesh instance 3D. Create a cylinder mesh and set the top and bottom radius to 0.4 and the height to 0.15. Then rotate it into the correct orientation and move the wheel mesh to the position where the rest distance is, so minus 0.5 in the Y. You can also favorite a property if you are using Godot 4.4. This will put the position always at the top in the inspector panel, which is very helpful. I'll put the material here just so it has some colors. Now copy the wheel mesh and paste it inside all the other Raycasts. And there it is. Now we have wheels. So let's hop back to the script and make some changes. The modification here is very simple. We need a new variable for the wheel radius, and we need to subtract the spring length with that. Now we just need to position the wheel visuals into the correct position. So first, let's rename all the wheels Instance Mesh 3D to wheel. Then we can find each Raycast wheels by calling suspensionray.getNodeWheel and change its position.y to minus the spring length. Using getNode each frame is not very good practice. We'll be changing that in the second part when we refactor the wheels into its own class. I have also added a debug arrow here that I made, just so we can see it better, but they are not needed. And let's also rename some nodes, so it's easier to read. In testing the game, our car has working wheels. Now, this Raycast car is completely physics-based, so to make the car collisions react properly, we want to make sure it has a proper mass value. Let's change the mass to 50 kilos and see what happens. Yeah, now our springs are too weak, so we need to adjust the spring strength, and That might have been too much. About 5,000 seems right. And to fix the bounce, we also increased the damping. While trying random values might be fun, there is an actual physics formula that can get us a range of damping values based on how springy we want our car to be. After rearranging the formula, we can get the damping value based on the mass and the spring force. It sounds complicated, but we basically just need to change the zeta value between 0 and 1 based on how damped the spring is, and we get a damping force for that. You can use the formula on Wolfram Alpha and change the values for the mass and spring strength to get the results. For very springy arcade cars, I found the values between 0.1 and 0.2 are very nice. But more realistic car suspensions will probably use values between 0.2 and 1.0. Now the last thing we need to do here is remove the pulling force of the car. To do that, let's just set the suspension rate.targetPosition.y to be minus the rest distance plus the wheel radius. This will make the Raycast works only on negative offsets, completely removing the pulling force. But because we don't have that pulling force anymore, now the car is a lot more bouncy, so we need to increase our damping force to counteract that. By changing the Raycast length dynamically, we can change the car's rest position at runtime and see its effect. And if we want to, we can add a small pulling force to the car, just enough to make it stick to the ground a bit. It's as easy as adding an offset here, that will allow the spring to extend over its rest distance. And we now got a small ground pulling force. But let's remove that. And that's it. That's the suspension part of the Raycast car done. Next part, we'll take a look at the acceleration of our car, and we will refactor the wheels into its own component to make custom modifications later easier. If you'd like to support me, you can get all the files used in these tutorials on Patreon. I hope you liked this video, and until next time.